In this what goes around comes around lab, we were using this rubber stopper and this hanging mass here connected to this string, which was connected to the rubber stopper going through this PVC pipe that allowed us to swing this around. And we kept this radial distance set to a 0.6 meters. And then what we were able to do is we were able to count the number of revolutions and measure the time using a stopwatch. And I have some sample data here where when I performed this lab, I was working by myself, so some error might occur, and you can see it on my graph, but I had the time 1, time 2, and I set up a spreadsheet here to calculate my average time, and then from that to calculate the average period, which was that average time divided by 10. I got the velocity getting 2 pi r divided by this period here, and that got me the velocity, and then I was able to square that velocity so that way I could relate the velocity back to the original force. And when I had that velocity with respect to the force, I'm able to get this graph. And on this graph, I have this 0.0268. That is the slope of this force versus the v squared. So with that, then I wanted us to plot on here. Our points, getting the force versus v squared. If you plot it, you can go between this 30 and the 100 for the v squared, going between 0 and 2.0 for the force. And then you should be able to see that some of your points will be above and below your line of best fit. And my line of best fit here just goes in between that data set. So to get to this analysis, when you calculate the slope, you have the change in y over the change in x. On the y-axis, we had force, so change in force over the change in this v squared. So you pick out 2 points on your line of best fit, and I'm using the slope I got from my spreadsheet of a 0.0268. Now for the units, I have force divided by v squared. Force is newtons, v squared is meters squared per second squared. Force is a newton, which is a kilogram, meter per second squared. So one of these meters cancels out with one of the squared meters below. The second squared cancels out with the second squared, giving me units of kilograms per meter. So I have a unit of mass divided by distance. So my slope here is this 0.0268 kilograms per meter. Using this mathematical model, I have y equals mx plus b. On the y-axis, I have force. On the x-axis, I have v squared. And my slope, which is my m, in this case with this m, is this 0.0268 kilograms per meter. Now I know mass is given with the variable m, and the only distance that we had here is this radial distance r. So the centripetal force, which was the purpose of this lab, we have mv squared on r. So we're able to have this m times our v squared divided by r, and that's how we're able to get to this centripetal force. So in this conclusion, I wanted you to be able to restate the purpose. The purpose was meant for us to find this equation for centripetal force. So the centripetal force is this mv squared on r. And then I want us to try to go into what is the real force making this go in a circle. So the real force for this lab was the force of tension because it was from a string. I want you to tell me what data was it that you needed to collect in order to find this mv squared on r. Because you didn't actually measure the mass of the rubber stopper. And then how does this relate to planetary motion? What is the force that causes a planet to go in a circle, or rather in orbit? So this is the part where I want us to try to get to for this conclusion.